All right, so we're analyzing the graphs of polynomials. A certain airliner has the following carry-on luggage requirements. The length of the carry-on. So obviously carry-on luggage is rectangular. It's a rectangular prism-ish. I know, we can argue against that, but that's the basic idea of what it is. So we're going to make that assumption here. The length of the carry-on must be 10 inches longer than the width. Okay, so length must be 10 inches longer than the width. The sum of the length, width, and height must be 40 inches. So length plus width plus height must be 40 inches. Now that's kind of weird to say exactly. What is the maximum possible volume of the carry-on? Okay, so we can obviously do a substitution here. Volume equals length times width times height, right? So that means volume, this is like my y value, is going to be the equivalent of, well, that's W plus 10 for length. We've got W for width. Now I'm going to take this second equation here that we've got and I'm going to solve it for H, which means two things are going to go to the other side, the width and the length. Well, before I do that, maybe I should do another substitution. Like this is going to come down in this equation. So I've got W plus 10 plus W plus H equals 40. Okay, now if I solve this thing for H, that would be H equals 40 minus 10 minus 2 W's, right? Because you're taking both of the W's over to the other side. Okay, so that means that H equals negative 2W plus 30. Now, yes, I know we can say 30 minus 2W if we wanted to, but I'm not going to. So negative 2W plus 30. Okay. So we're going to treat W as my X value. And I am not going to FOIL this, okay? Let me give you a reason. Since I'm being asked to find the max volume, this is a Desmos graphing calc question. Therefore, why waste the time to FOIL all that together? Desmos can graph it. Whoa, can't spell. Without me doing that. Really struggling. Now I would say this is critical. It does like X and Y for variables. So if I started throwing in V for volume and W for width, it would get, it would start questioning. Okay, what is this? What is this? Okay, so let's get this thing graphed. Now, as you can see, I typed it in exactly the way we have it written, and I get this picture that doesn't make a whole lot of sense. This is when you need to start paying attention to how I am adjusting it. So put 2 fingers, I'm going to put them on the x-axis and stretch this out only in the x direction. I still don't have a good picture, so I may have to shrink it in the y direction. And it still looks like some sort of, unusual looking shape until I get it to here. Now, notice that I've got, this is not as stretched out. This is majorly, we did a big shrink on the vertical so you could see more of it. All right. Now, what part of the graph, the next question we have to ask ourselves, what part of the graph makes sense? What part of the graph will help us answer the question? Well, anything with a negative is a no-go. Let me show you what I mean. So, it can't have negative x's and it can't have negative y's. So, that means this section is useless to me. This section is useless to me. This section is useless to me. There is only one section of this graph that has all positives. And it's this little hill in the middle. So the question is, what's the maximum volume? Well, isn't this x, which is technically the width? And this is y, which is technically the volume. So the max volume would be found like right there at the top of that little hill. And that's what we call a relative, right? Relative max. And you know that relative maxes are y values, so don't make them out like they're anything else, right? So the cool thing about Desmos is I don't have to do a whole lot of work to find it. I click on it. Now, you need to be smart enough to know what it is you're looking at. Yeah, I know. It does all the fancy calculations for you. Okay. No part that includes negative numbers for either width or volume. So, what are we looking at? The max volume is 2052.205. Now, obviously, I'm rounding to the thousands, but we would find the max volume. Now, when does that happen? If the width is 8.932, something like that, if you want to round to the thousands there. So I'll have to go back and look at the question to see what they're asking me. Did they only ask me for the max volume, or did they want me to give all the dimensions and the max volume? So let's go back and look. What is the maximum possible volume of the carry-on? Well, so they didn't ask me for all the dimensions, although it would not be that hard for me to plug the width back in and find all those other things, because realistically, it's, you would want to know that. However, that is the max volume, 2052.205. Okay? So that takes care of this question. But it's a Desmos question. You just have to know what part of the graph makes sense to use. Metalworker wants to make an open box from a sheet of metal by cutting equal squares from each corner as shown. Write an expression for each length. Well, the original length was 11. But remember, you're going to cut an X away from both of the ends. So that makes my new length 11 minus 2x. Well, same thing with the width, right? The 9, right? So that's going to make a width of 9 minus 2x. Of course, when you fold everything up, what's the height of the box? Well, the height of the box is just plain old x. So, oops. Come on. There we go. That's what we call that. So the volume would be when you and notice that they said factored form, right? That's the golden words, in factored form, so I don't have to actually put this in standard form. And then we're going to go graph this here in a minute. Okay, so we have our equation graphed, but we don't exactly have a great window. Now remember, I'm going to use my 2 fingers on the x-axis, kind of expand, maybe shrink the whole thing down, and oh, now I see a pretty good looking picture. I can stretch it out a little bit more on the x-axis, but you got to get it to the point where you have a good looking picture. And then we want to know what part of this graph makes any bit of sense here. So take a snapshot. They're asking me to come up with, let's see, how do they say it? Can I grab this thing and move it? Graph the function using your calculator or Desmos. Find the maximum volume of the box and the height of the box that generates the maximum volume. Okay, so X represents the height. It's the amount that's going to get cut out of the corners. Anything with a negative volume doesn't make sense. A negative volume or a negative height. Right? This is height. This is volume. But this part of the graph doesn't make sense either. We just can't keep cutting an infinite amount of space out of the box and get an infinite volume. This is the only section of the graph that makes any bit of sense, and whatever that relative max is up there at the top, that is going to be my highest volume. And it will also tell me what the x is that goes with it. So let's go ahead and find it. We go back to Desmos. We locate that single point. We have the answer to both of our questions. The maximum height, which is the x value that should be cut out of the corners, 1.642. And the maximum volume, 72.420. So now we know exactly how much to cut out of the corners, and we know that that will generate us the most volume of any possible box. The height of a pod's moving container is 4 feet less than the width. Okay, so we've got a pod. The height is 4 feet less than the width. Okay, so here's the width, so the height would be 4 less than that. W minus 4. The length is 9 feet longer than the width. Okay, so W plus 9. So length W plus 9. Oh, I can't write W plus 9 there. They actually want the numbers. Write a formula for the volume. V equals, we're going to do it in factored form again. W minus 4, W plus 9. Now, is there any magic order in which I put those coordinates? No. You can put them in whatever order you want to put them in. Now let's go to the graph. All right, so probably going to go back to the beginning. And we've got our equation typed in. Remember, you use x's for, where W for the width and Y for the volume. And now we'll try to separate this and get ourselves a nice, gotta get 2 fingers on the Y. Boy, it's really being difficulty. 2 fingers, oops, try to squeeze it down a little bit. Now I get a better look at picture. Okay. I am really confused. Length is 9 feet longer than the width. Oh, the volume of the container is 336. I didn't consider that. Oh, okay. Well, that makes sense. So, what if I took that information and I made a separate equation? Volume equals 336. So now I could literally come here and say y, that's my volume, equals 336. What we want is the intersection point of the two graphs. So the graph is telling me x in our case represents the width, right? That's the x. And we just found out that it was 7 according to my graph. All right. So 4 less than that would be the height, 3. But 9 feet longer than the 7 is 16. So those are the dimensions of my pod to get a volume of 336. Now, there is another way we could have done this question. Suppose we took our equation. Here, I'm gonna shut these off so you don't see them on the graph. Suppose I took my equation and I subtracted, sorry, it's the same thing, x minus 4, x plus 9. Yeah, type. But I said minus 336. Minus 336. Now you'll see my picture, right? Here's my picture. In this case, I would be looking for when it equals 0. So in other words, I would want the x-intercept. So here's the x-axis. Here's the picture of the graph subtracting the 336. And look right there. There's the answer to the question. The width is 7. So that is a different way to do the same question. So I can either put the 336 and the volume equation and see where they cross here, or drop the equation down, drop the line down, and I will get the exact same answer of 7. Two different ways to do the same thing. Cat carrier, 2 feet longer than it is wide. 2 feet longer than it is wide. 1 foot shorter than it is wide. Volume is 15, so we're going to have two different formulas. One is going to be just y equals 15, and the other is going to be x times x plus 2 times x minus 1. I'm just replacing the w's with x's so I can go straight to my Desmos. Y equals 15, better use my zoomed in version, and y equals x plus 2 x minus 1. Okay, so we're looking at this, not a horrible looking picture. But we want to know where they cross, so it's a matter of just clicking on where they cross. So 2.411. So we should go with a width of 2.411. We should go with a height of 1.411. And we should go with a length of 4.411. So let the calculator do the work. That is one of the reasons why we like technology, is because of its graphing power and how it can find those coordinates fast, and then we can find intersections quickly. It makes some things in life very, very quick.